It's time for chemistry to come clean with you. Up till now, you've probably been told that water does not conduct electricity. Pure water does not conduct electricity. And that's not necessarily true. Pure water, no matter how pure it is, actually still conducts a very minute, infinitesimally small amount of electricity. So in class, when I say that water does not conduct electricity, what I should say is water does not conduct electricity to an appreciable extent. It's not as though water can conduct electricity enough to kill you or even really give you any sort of shock. However, it is conducting a minute or small amount of electricity. And the reason that water does conduct electricity, or the fact that it does conduct electricity, no matter how pure it is, proves that water self-ionizes, meaning water will break down into hydronium ions and hydroxide ions, or hydrogen ions and hydroxide ions. However, it does it in an extremely small amount. Only 2 in every billion water molecules actually ionize at any particular instant. So it's a very, very small amount. Water's ability to be both an acid and a base, water's ability to produce hydroxide and hydronium ions, is what we call amphoteric. It can be both an acid or a base. If we were to write the equilibrium constant or equilibrium mass expression for this above reaction, since water is a pure liquid, we would not include it. So K, or Kw, which is the auto-ionization constant for water, would simply equal the concentration of hydronium ions times the concentration of hydroxide ions. And in pure water, or in water, this has a set value. It's 1 times 10 to the negative 14th. If we know this, we can determine the concentration of hydronium and hydroxide ions. If you think of each one as being equal, because water is breaking down into each one in equal quantities, so this would really be Kw equals x squared, we can determine that the absolute value, we can determine that the concentration of hydronium and hydrogen ions in pure water at any given time, if it's neutral, meaning there's an equal concentration of each, is the square root of 1 times 10 to the negative 14th, which comes out to be 1 times 10 to the negative 7th. So if the concentration of hydrogen ions equals the concentration of hydroxide ions, we're in what's called a neutral solution, or that which is equivalent to water. If the concentration of hydroxide of the hydrogen ions, the hydronium ions, is greater, then that means that something is contributing those hydroxide ions to the solution, and therefore we must have an acid present. So we are in an acidic solution. If the concentration of hydroxide ions is greater, then something is contributing hydroxide ions to the solution, and therefore we must be in a basic solution. This relationship between hydrogen, hydroxide, and water, or Kw, is the basis for the pH scale. So before we go over pH scale, let's talk about pH in general. Let's review some of the things you should hopefully know from first semester chemistry. The pH scale is a continuum, with pure water being in the center. And as you become more and more acidic, you go towards the left. And as you become more and more basic, you go towards the right. It's alphabetical. Acid on this side, base on that side. Something that is neutral, so for, well, water being the base of, or being the basis of the scale, is found in the middle. You probably know that things that are basic are 7, have a pH of 7. As you move, as you get lower than 7, you become more and more acidic. So strong acids are found at the bottom of the scale, and weak acids are found closer to 7. The opposite is true. As you get more and more greater than 7, you become more and more basic because the concentration of hydroxide ions increases. So the weaker the base is, the closer it is to 7. The stronger it is, the further it is from 7. Now what does that 7 mean? Well, if you were really good and you were paying attention in first semester chemistry, you know that the pH scale is based on a logarithmic scale. And pH is simply the negative log of the concentration of hydrogen. What does log mean? Log is really just a fancy way of saying, what is 10 raised to? What do you have to raise 10 to in order to get this number? So let's think of it as, well, first off, let's talk about what you could raise 10 to. Let's do 10 to the negative 1, 10 to the 0, 10 to the first, and 10 to the second. Each of these numbers has a corresponding number that goes with them. 10 to the negative first means simply move the decimal place and you've got 0.1. Anything to the 0 is 1, 10 to the first is 10, and 10 to the second is 100. Those would be what the log of each one of these were. The log of 10 to the negative 1 would be 0.1. Oh, I said that backwards. The log of 0.1 would be negative 1 because 10 is raised to the negative 1. The log of 1 would be 0 because 10 is raised to the 0. The log of 10 would be 1 because 10 is being raised to the first. The log of 100 would be 10 is raised to the second to get 100. So what do you think the log of your age would be? Chances are you're 17, which means you're 10 to the first and some change. So I would guess, go ahead and make a guess. What would you think your log would be? It would be somewhere like probably 10.1, 10.2. Let's guess is your log. That the log of your age is 10.2. Let's guess. Meaning that if I was going to predict what I would raise 10 to in order to get 17, I'd predict somewhere between 10.2. Because you're nowhere near 100, right? Because 17 is not anywhere near 100. So this little decimal point is going to make some minute difference. So the log of 17 is 1.23. We're pretty on the money. What about my age? I'm 26. What do we predict that my log is going to be, the log of my age? It's probably going to be greater than yours, so greater than 1.2. Let's say maybe 1.3. So the log of 26. Oh, 1.4, I feel really old now. But as we get closer and closer to 100, as we get closer and closer of having to raise 10 to the second to get our years, that decimal point will continue to increase. So an increase in logs, an increase of just 1 in your logarithmic scale, or in your pH, is an increase of a magnitude, an entire magnitude. So if I go from having a pH of 3 to having a pH of 2, I've increased the concentration of hydrogen 10 times over. And just like you can have a pH, you can also have what's called a pOH, which is simply the negative log of the concentration of hydroxide. And since Kw equals 1 times 10 to the negative 14, so Kw, the log of Kw would be, or the pKw, I guess you could call it, even though it's not a real thing, would be the negative 14, so we would call that 14. Kw equals, the pKw equals 14, which is what the pH scale is based off of. And if you have a log times a log, you can simply add the p's together. So pH plus pOH equals 14. So if you're given one, you can find the other by knowing that together they have to equal 14. If you're given a concentration, you can find pH. If you're given a concentration of hydroxide, you can find pOH. Or you can know that together hydroxide plus hydrogen, or times hydrogen, the concentration of hydroxide times the concentration of hydrogen has to equal 1 times 10 to the negative 14. Now, you'll notice that the pH scale, I have made sure to include that they have arrows at the end of each one of these. That's because this is a continuum. The pH scale that you have been taught, most likely, you know that it goes from 0 to 14. But that's not necessarily true either. You can have pHs that are well below 0, such as concentrated acids. Concentrated sulfuric acid has a molarity of 18 molar. And if you went ahead and calculated the pH of that, you'll find that it is well below 0. So the pH scale that you learned in first year chemistry or learned in middle school, going from 0 to 14, that's pretty good if you're dealing with unconcentrated, if you're dealing like 1 molar. But once you get past 1 molar, it kind of falls apart. It's not between 0 and 14. It's a continuum. It goes on forever. But 7 is the middle point, where everything is neutral. So just for giggles, just to express this point, let's say I have a liter of 18 molar concentrated sulfuric acid. Sulfuric acid, being a strong acid, is going to dissociate completely, leaving me with 2 hydrogen ions and a hydroxide ion, sulfate ion. Initially, I have 18 molar, and since I have 1 liter, I have 18.1 moles. Since it dissociates completely, I'm going to lose all of this, and my equilibrium, even though it's not really going to establish one, well, it might establish one, insignificantly small. I'm going to have 0, or when I end, 36.2 moles of, well, molar in this case, since I have 1 liter, of hydrogen ions and 18.1 molar sulfate ions. But it's just the hydrogen I'm interested in because I want to know what the pH is. So pH equals the negative log of the concentration of hydrogen, which we now know is 36.2. So if I put that in my calculator, negative log of 36.2, I find that the pH is negative 1.56. Let's talk about sig figs. Sig figs get a little iffy when you're dealing with acids and bases. However, you're going to use the same rules that you used before. You go off of the least accurate measurement in everything that you're given. I gave you 18.1, so you should zoom in and say that is 3 sig figs. My answer can only have 3 sig figs. If I had something else if I said it was 1.0 liters, that's only 2 sig figs, so my answer should have been 1.6 if I gave it to you that way. But since 1.81 is the only number I gave you, I would say that that is what you would base your answer off of. So go off of the least number of sig figs. Sorry, not sig figs. The least number of decimal places. So this has 1 decimal place. Oh, I'm wrong. So this should be reported as 1.6. Least number of decimal places. So I was calculating the pH of a strong acid. And if you were doing a strong base, you would find the pOH and then backtrack or subtract from 14 to get the pH. In the case of a weak acid or base where an equilibrium is established, it's a little more difficult, but not nearly as hard as the equilibrium unit. The general format for a weak acid breaking apart is hydrogen and some anion breaking apart into hydrogen ions and anions. Pay attention to the stoichiometry. However, remember that acids can only donate 1 hydrogen at a time, and therefore you typically will only lose 1 hydrogen at a time. In the case of a strong acid, that's not always the case, but in the case of a weak acid, you're only going to lose 1 hydrogen. A weak base is also going to establish the equilibrium, except for in this case you're going to get hydroxide ions. However, either way that you do it, you'll come up with the same general format. You'll set up a rice table just like we've been doing for the equilibrium unit. Do you have to do the rice table? No. If you know how these always look, power to you. But if you don't, I'm going to show you. So here's the beginning of a rice table. You have the molarity initially, and initially you have 0 concentration for each ion. Same thing over here. And in terms of X, you've got this. Now, no matter which one you have, it's going to come out to be the same thing. Ka or Kb equals x squared over the initial concentration minus x. But as I taught you in the equilibrium unit, you should always write what K equals. So K equals concentration of hydrogen ions times the anion divided by the initial, the acid. They'll both have the same general format. It'll be x squared, x times x is x squared, divided by the initial concentration minus x. Now in the equilibrium unit, when you got this, you knew you had a quadratic formula in your future. You had to take this expression down here and multiply it by k, and then you got this huge thing, like in this case it would be 1.1 times 10 to the negative fifth minus 1 times 10 to the negative fifth x, if the initial concentration was 1. And then you had to solve for x by using your calculator. However, since 2010, the AP exam doesn't usually ask quadratic problems of acid and base problems. And it doesn't usually do it also for equilibrium problems. That does not mean you don't need to know it. If you do, if you can't do this next step I'm about to show you, you do have to go through the quadratic formula. You have to be able to drive your calculator and figure it out. However, let's look at this problem, or these problems. In this case, Ka and Kb, for either one, let's just look at Ka to begin with. Let's just look at Ka. Ka is a very small number. If this initial concentration is much greater than 100 times Ka, then it doesn't matter what X is, because it's not going to make a substantial difference in the initial concentration. Let's say the concentration in this case is 1. If the initial concentration here is 1, if I went through this whole problem and I put it into the calculator, I would find that X equals 0.03. So even if I subtracted 0.03 from 1, according to significant figures, I'm still going to come up with 1. It's going to be 0.997, which is still going to round to 1. So this is not going to be a substantial difference in the concentration of M, or of the initial concentration. And so we can say we're going to ignore X. And when we neglect X, it just makes it that much easier for us to solve. We would take K, multiply it by the initial concentration, and take the square root, and we would find the concentration of hydrogen ions. So when you're given one of these problems, you're either going to solve for X when you're given Ka or Kb, or you're going to solve for Ka and Kb when you're given X. And usually when that comes about, it will be based on information from a previous problem. Once you have the concentration of hydrogen, you can find the pH. Once you have the pH, you can find the pOH. If you have the concentration of hydroxides, you can find the pOH, and you can find the pH. We're going to be doing these in class, next class. And we will also discuss calculating the pH of weak acid mixtures. When you're calculating the pH of a weak acid mixture, the acid with the greatest Ka is the one that does the driving. It's the one that decides how things are going to work, because it's like a common ion effect. We will go over it next class.